Good afternoon, everyone, and really happy to have you here at IIT as part of Paradox 2022. Okay, this online degree, the BSc, is a big experiment from our side as well, and we really hope that it works out successfully. I mean, the whole point is that we would like to reach as many learners as possible, and hopefully there is something that we can also contribute, which is in some ways at least better than what you might find outside. Okay. So a little bit of background about myself, what I am doing over here. I actually have very little to do with application development or for that matter data science. Okay. My background is in electrical engineering. I am a professor of electrical engineering. By the way, my name is Nitin Chandrachoodan. I hope you all know that, otherwise you're in the wrong room. I am from the electrical engineering department, right? And my area of research is primarily in VLSI, embedded systems, digital design, okay, primarily those topics. And as part of that, I end up having to write code, which is mostly, and it's a mix of different languages. There are some parts that need to be done with language like Python. There are others where I need to use hardware description languages like Verilog, okay. There are yet others where I need to write C code, right, which either runs on a microprocessor or in some cases on an embedded system. And in some cases, at least one or two, I have actually had to develop web apps, okay, which ultimately was what led to my teaching the course on application development 1 and 2, okay. But what I hope that means is that that also brings a different perspective on the whole idea of application development. So I'm not looking at it purely as a software engineer. I'm trying to look at it from a different point of view. And to some extent, what I would like to do today is also try and convey that to some extent. Okay. In other words, what I'm trying to talk about over here is some ideas that are not directly part of data science or part of engineering in some way, but are sort of powerful abstractions, right, that help you to sort of think about the way you design systems differently, and hopefully that will make a difference to the way that you go about implementing certain things, okay. So it's nice to have a small class. I mean, this is a relatively small classroom, right? At least I can see all the way to the back and I can see each of your faces. So please feel free to ask questions at any point, okay. This is supposed to be a workshop, not exactly a lecture. And to be frank, my preparation, my slides are very poor, as you will see, right. More of what I have is something where I'll be writing, showing a little bit of code, but I think the real sort of where this workshop is likely to become interesting is if you have any questions. So at any point, feel free to just raise your hand, interrupt me and ask questions, okay. It's a small enough classroom that I think we can do that comfortably. Okay, so let's get into the topic for today, right. So what I'm going to do is sort of take a journey through 4 different topics that on their surface at least are unconnected in any way, okay. And what I hope to do is try and show you in what way there is a connection between all of these, right, and how the way that you think about a problem could actually affect how you go about trying to solve it, okay. So I'll start by taking one example, which is log file analysis, okay, and I'm saying the Unix shell because there is something about the Unix shell that we will actually be using in order to try and benefit, and go about the way that we go about doing the analysis of the logs, okay. The next thing that I'll be doing is more from my background, okay. It's a electrical engineering problem in the sense that it's more signal processing and communications, okay. But what I will be doing is showing how a sort of modern high-speed communication system also broadly starts to look similar depending on how you approach the problem and what you are thinking about it, okay. Then another one which is hopefully more relevant to you as students of data science, right, a neural network, okay. And what I'm going to do over here is take a couple of examples of what neural networks, common neural networks look like, show you once again why they also end up having similar properties to what the other things that we have considered before. And finally, app dev has to come in somewhere, right? I mean, after all, I taught that course. So I'll also look at a little bit at the overall infrastructure of a web application and from the same point of view. What I want to do at the end of it is to sort of try and abstract out and say, okay, what are the commonalities? What is it that actually led us to this way of approaching or solving certain problems? Okay. So the first problem, so to say, right, analyzing web server logs. The first question is, what is a log file? Okay. And over here, essentially what we have is something like this. Now, all of you know what a website is, in the sense that you have definitely visited websites, right? If not, written a web application of your own. Okay. So what you normally would do as a user would be, you are sitting at your desktop or laptop, right, connected to some network, right, which usually we also end up calling the cloud, right, for the simple reason that once the packets of data from your machine reach that network, it is very vague and fuzzy where exactly it's going, how it is going, right? You don't have much control over that. The best way to sort of visualize it is to think of it all as one amorphous cloud of multiple different servers, and somebody somewhere is responding to your requests. Okay. But what actually happens in practice is, there's a server, right? And what the server is doing is, it's ending up getting requests from your machine, right? And in this case, normally what I would do is, I would refer to the browser that's running on your machine as the client, right? The end client is of course you as the user, right? But as far as the network is concerned, the actual client in this case is the browser, which is issuing requests. Okay. So what does a request look like? It's just a packet of information which basically says, okay, I want something. It basically has the name of a file or something else that needs to be retrieved from the server and returned back to you. Okay. Now, one of the things that, as a person who manages servers, right, what you would probably like to do is keep track of how many people are coming to your website. Okay. So you want to know how many people are coming, how often are they coming, which pages are they trying to access, right, what are they downloading. All that kind of information is useful as a webmaster, right? Why? Because of a few different things. One is, you just want to understand traffic patterns. Is the traffic more during the daytime? Is it more at night? Does it sort of spike before exams? Is it, or if you're maybe having a bank or something like that, when is it that the traffic suddenly shoots up, right? You issued a new loan scheme and the traffic goes up. All of that is useful information, right? The other possibility is, somebody is trying to attack you. Somebody is trying to hack into your website. Okay. How do you detect that? Once again, if you are maintaining logs, you would probably say, okay, look, I know what the normal traffic at a given time of day looks like. I would like to detect in real time, if possible, changes in that traffic. Okay. And of course, finally, the one very useful thing over here is, I can also tune. As a webmaster, even assuming that nothing else is happening, there is nothing untoward, right? My traffic is going along well. The next question I should probably be asking is, look, is my server infrastructure adequate? Is it oversized? Is there something wrong over here? Have I put in too much? Should I be sort of trimming something out, and so on? Okay. So all of this tuning, performance improvements, all of that comes about by essentially storing logs of information. Okay. So when I say logs, it is just some small piece of data which indicates what was being requested. Okay. So what I have shown over here, and I'll show you this again in a moment, is actually direct logs from the NPTEL server. Okay. So most of you have probably seen the NPTEL website. The NPTEL website is actually split into multiple things, right? We have one which serves the front end, which you actually see, where you can go see the courses and so on. And there is also another sort of data server, so to say, right, which is hosted in our data center in IIT Madras, right? And so if you, for example, want to view the videos of NPTEL lectures, there are two options. One is, you go to YouTube, right, and most of the time the links are there on YouTube. The other option is that you can actually directly get an MP4 file from the NPTEL website. Okay. And all those MP4 files are actually stored on this server, which is sitting in our data center. What I'm showing you here are the logs from that file from, well, day before yesterday, okay, 18th May, right? So all these numbers are actually correct, right? What you can see over here is this is roughly the structure of a log file. This, what information is it? The IP address from which the request came, right? So the client, in other words, you are a client somewhere, right? Either on your phone or a tab or a laptop or whatever it is, you are trying to access this, in this case, a PDF file, right? And what it does is it logs the IP address, it logs the time, right, when that request came. This get over here is the type of request, right? So in this case, all that you are doing is retrieving data, right? There are other types of requests. Those who have done app dev would of course know that, there is post and there are also put and delete and others. Get and post are probably the most common. In our case, it's mostly get. Why? Because like I said, this is mostly a data server. Okay, I'm just I have a huge amount of data out there, static files, and as and when somebody wants to retrieve it, just throw it back over the pipe at them. Okay, this long string out here is the actual path to the file, right? Literally what it's going to do is go look up that thing. The server has to go fetch that file and send it back. There is some additional information such as which version of the HTTP protocol is being used. There is this 200 out here is the status code, right, saying did it succeed or not. Okay, this I believe is the number of bytes that were returned. Okay, and if you actually look at it in one of the other cases, you might see that there are some additional strings out here, right? So there is something out here which is called the referrer, right? Where did I get this link from? Okay, in other words, I have gone and clicked on some link in order to download a PDF file or something else, but did I get that link directly? Was it indexed by Google? Was it from Microsoft? Was it from some other random website? That information is also useful to me as someone who's managing the website. And finally, this part which I've trimmed out over here is something called the user agent, right, which actually contains information about which browser you used. Is it Chrome? Is it Safari on Apple? Is it something else, or is it just some fake browser string that you have created? You can change this, right? So this is not in any way kind of a foolproof way of determining where you came from, right? Now, what I would like to do as a person who's managing this website is to say, can I find out who are the most common, who made the maximum number of requests to my website? Okay, that's one possible question. There might be others. For example, I might be interested in saying, okay, which was the most commonly requested page? One thing I should probably really pay attention to is, am I seeing a lot of errors? In other words, a 200 status code is fine, 404 is probably not good, 500 is definitely bad news, because 500 means the server had an error, right? 404 means that the file was not found. Why did that happen? Why are people going on requesting files that don't exist? Okay, so at least as a the person managing the website, I need to pay attention to this, right? There might be some pathological cases, right, where people just go and access links, right? So the so-called crawlers, web crawlers that are trying to index files, they might end up, if they are badly written, trying to just access files that do not exist. Okay, so there are some things that are out of your control, but there are things where at least if you notice that errors are creeping up, why did that happen? Did anything change recently, right? So you should be sort of constantly paying attention to this. All right, so that's the background, that's the motivation for why you want to do log server analysis. The obvious next question is, how do you do it? Okay, so in this case, right, you can see that the logs are actually poorly structured. What I mean by poorly structured is each of these log entries is just one long string of text. Okay, it has a bunch of digits in the beginning with digits and dots, right? Then there are these two dashes, which actually I don't even remember why they are there. I think it's something to do with authentication, right? After that comes the date, which is in a human readable format, but for a log file, I don't necessarily want it to be human readable. I want a computer to be able to process it. Okay, so is this really the best format I could use? I don't know. The get request, the file name, all of those are clubbed together into one big string. Okay, things like this user agent, for example, are a nightmare because it's just a string which has like spaces inside it. I can't really make much sense of the whole thing. Okay, so this is an example of what is actually not a great log format to use, right? But it's been used with the Apache web server since probably, I don't know, 1994 or something like that, right? So it's here to stay. Okay, people use it all the time. Of course, in more modern web applications and web servers, you have different kinds of logs also that you can generate, right? So if you go look at what Google App Engine does, they might display the logs to you in something looking like this, but internally they store it quite differently. Okay. So all right, all that is background. So you could, for example, also use something like a JSON or some kind of a structured format in order to actually give meaning to this data, right? So the fact that this 200 is an error code and can be only one of a few different parameters, this number should always be an integer, a number of bytes, right? And it has to be non-negative. Certain kinds of sort of properties you can associate with each of these things, which will make it easier to validate whether these logs are actually useful or not. Okay. All right. So with all this in mind, I'm going to take a couple of examples of how I might go about analyzing these logs. Okay. So let me switch over to this, and please let me know if the font is readable at the back. Can you read what is here on the screen, or do you need it to be bigger? It's readable? All right, good. Okay, so like I said, this is what a log file looks like. Wall of text. Okay, I can't really do any coloring or formatting to make it look any better. This is what it is. Okay, but you can see that each line over here basically is one long piece of information, right? So it starts with this IP address, goes through the date, blah blah blah. You have this string out here which is the actual user ID, and it goes all the way till here. Okay, no specific length on the limit on the length of the string, but that's okay. You probably don't care too much about that. So I'm going to show you one code that I wrote in Python that unfortunately the colors are poor. Yes, better. Okay, so at least it's readable at this point. Okay. All right. So what have I done? I have basically tried to create a Python file which literally does it the way that you would think about parsing a log file like this, right? So what do I mean by parsing in this case? And normally parsing means you take something like a program, a C program or a Python program, read it line by line, split it up into words, and try and associate meaning with those words, right? So the parsing is the first part which just says, okay, I'm going to read it in, check whether it is grammatically correct, right, syntactically correct, and probably generate some errors or if it is not, or just somehow break it up into something that can be used. Okay, that's pretty much what I'm trying to do over here. Of course, my syntax in this case is very simple. I basically have space separated blocks. Okay, so what I'm going to do is, the approach that I'm saying is, I want to find out the most common request source, okay, the IP from which the maximum number of requests came. Okay, how would I do that? Let's try this approach. I create a dictionary. Okay, so H is equal to these open brackets basically creates a dictionary. I then open this file. Okay, so I'm hard coding stuff here. This is not normally how I would want to do it, right? I should probably accept the file name as something coming in from standard input or one of the parameters. Doesn't matter. For now, I'm just hard coding it. And then I go through each line, just split the line wherever I see a space, okay, and pick up the element number 0 from there. Okay, why element number 0? Because I know that the IP address is the first entry out here. Now, if the element is not already in the dictionary, set the number of times I have seen it, the count basically equal to 1. Okay, it's a sort of histogram or a count that I'm creating, right? Else I set it to that +1, whatever value it had, +1. Right, so far so good. I mean, it's done, right? It's already taken care of. I mean, so by the time I'm done with this loop out here, the entire work that I needed to do for finding out how many times each IP was seen in the log is completed. After that, what I want to do is I want to actually sort it, right? So this particular piece of code is, I mean, frankly, when I come up with something like this, I need to go on Stack Overflow and look for how to do this, get the values from a list in sorted order, right? So you do that, right? You basically find out how do I get the list values in sorted order, and this is something which basically says it takes all the item values, the keys, right, and sorts them and returns a dictionary which contains that same thing, but now with the sorting done on item of 1, that is to say on the second parameter, the number of times it was hit. And all that I'm going to do is just print that out over here. Okay. So what would happen if I actually ran this through over here? I would see that okay, right, and it ran pretty fast, right, the whole thing completed within like a fraction of a second, okay. And you can see, for example, that this IP address has visited our website 6,500 times in one day, right. What does that mean? It's not like, you know, somebody was actually coming and doing it. It just means that they probably had either a browser or in some cases a script that was just trying to download a huge amount of data from our page, okay. This IP on the other hand had some other number and so on, okay, very good. The question then comes, okay, what happens if I, yeah, sorry about this, yeah, what if I want to change not the IP address, but let's say which file was requested the most, okay. What should I do then? I probably want to then say, instead of split of 0, right, go pick up the entry corresponding to the file name that was being requested, okay, and that should work. This style of coding is what I would normally call an imperative style, okay, and the reason I am saying imperative is I am literally thinking, okay, what should the computer do? Read in the file, take it line by line, split the lines, look at it, put a entry over there, a dictionary, a counter table, and keep incrementing values, okay. It works. If I need to modify something, I can go back and change something over there, right, and everything actually works out reasonably well, right. Now there is an alternative, obviously, which I am getting at, right, in a very roundabout way, which is to say, let's try and look at what are the properties or what are the tools that are already available to us once you have a Linux system, okay. And what I would say over there is, you know, I have this log file. What do I want to do? I want to get the first entry from that log file, the first set of values, okay. It turns out there is a command in Unix which does that for you, okay, and that command is cut, okay. So I can cut -d, this space over here basically says use this space as a delimiter, and then I say I want the first field, okay. Now look at what I have done. I have given nptel.log as the name of the file, okay, but there was another way that I could have done it, which is to say that I will actually take the nptel.log, use the cat command, right. What does cat do? Something very trivial. It just reads a file and again puts it out onto the output, okay. So on the face of it, cat is one of those useless tools. It just takes a file and then puts it onto the screen, okay. Why do you want that? You have editors. It can't edit, it can't do anything else. It can only take a file and put it onto the screen. It's actually not putting it onto the screen, it's putting it onto something called the standard output, okay. The good thing about the standard output and the Unix philosophy in some senses, I can use this pipe, okay. So this vertical bar is what is called the pipe in Linux, right. I am saying Linux, the point is it existed well before Linux, right. So it's part of the so-called Unix philosophy, right. And if you go look up on Wikipedia what is the Unix philosophy, you will see that there are some very nice principles out there. The most important one is each program should do one thing well, okay, and the second one is programs should generate data in a form that can be consumed by other programs, okay. That is essentially what you are seeing here. This cat program is doing only one thing, reading a file and putting it onto standard output. What the cut program does is it accepts data from standard input, does something with it, in this case taking out the first element, and puts it out onto its standard output, okay. So if I run this, I will find that, you know, a whole lot of data just whizzed past, but that is every single first entry in every file over here, okay. Now one additional thing, so how many log entries do you think were there in that file? If you don't write the cut over there, then it will just do the same, you know, the whole thing will come out onto the screen, right. It's just too much garbage, huh? Nothing. I mean, it just takes whatever it saw and puts it back onto the screen, okay. But with the cut, what it does is it puts out only that first entry out there. Now this is useful, yes, but it's not good enough for me. Now what I want to do is I want to find out which of those entries was the most common. How do you think you could do that? Right, so probably the simplest thing to do is put it through a sort command, right. Sort is another one of those utilities that is present in Unix systems. what happens when I sort it? It sorts and prints it out. Okay, so the thing that you can see is, all the things over here start with 9, right? So at least it is not done a numerical sorting, it's actually considered them as strings and just gone ahead and sorted everything. Okay, all right, good news. Then what else? But sorting is still not good enough. Okay, I wanted to start grouping things together. There's another command for that called unique. Okay, but unique will only sort of say, okay, this IP is there some 8 times, I will only print it once. That's not exactly what I want. I want it to print how many times. Okay, so unique takes a flag -c, which will actually tell you how many times it printed. Okay, right, this looks a lot better, right? I do this and now it's showing me all of these entries out here. This IP, for example, right, had 42 hits, this last one had 8 hits and so on. Okay, can I clean it up a little further? Sure, put it through sort once again, right? But now sort -n, meaning that treat these values as numbers and sort them rather than as strings. Okay, what happens when I sort like this? There you go, you got the answer, right? So in other words, this IP address came 6551 times, this IP address came 4858 times, exactly the same numbers as what the Python script generated, right? You can run it again to verify that. Sorry? Yeah, good point. So, the sort is on the first column by default. If I wanted to do another column, I could have given something like nk2. In this case, that will probably be an error because the second column is actually not a number. I am telling it to treat it as a number and sort it. It will still do something, but it will do something weird out there, right? But yeah, ideally I should have given nk1, that is to say the first key, right? And that should give you this same answer. But yeah, by default it sorts on the first column. Number of hits, right? See, because what has happened, this 6551 did not come from my log file directly. It came because of this unique -c, right? That was the command that actually counted the number of times it saw that particular IP address. This is on one day, yeah, on one particular day. Yes, it might have been different pages, it might have been, see what happens is for certain things, especially like MP4 files and so on, there is something called a partial download, right? So rather than trying to download all the 100 and odd megabytes of data at once, it will download a little bit, the connection breaks, it then has to resume the download. So then it does another partial download, each of those gets counted as a separate hit. Right, so that could be one reason why you are ending up with 6,000 hits and so on, because otherwise, I mean, manually it's not possible for a person to do this.
Can also be multiple computers on the same local area.
It could be, exactly, right? So for example, IIT has a small pool of IP addresses. So if someone from, the entire 10,000 students sitting inside the campus are going to a particular page, they will all see, let's say, around 30 or 40 IPs. And suddenly the webmaster at that end might feel this IP is trying to attack us in some way, right? And that has happened in the past. So things like journals, IEEE Explore, ACM, Digital Library and so on have actually sort of, sorry? Yeah, so multiple users might be trying to access the same website or the same page, right? They will all end up coming from the same IP. So that's possible. That depends on the website. So yeah, like I said, journals, for example, have a policy like that, right? If they find that there are too many hits from the same IP within a short amount of time, they consider it not so much as an attack, but as somebody who's trying to do a mass download. So see, IEEE Explore, for example, they have IIT has a paid subscription, right? But what happens with that paid subscription is that you are expected to manually go and download. I mean, you can read as many papers as you want. But if you write a program that tries to download all of them, that's against their terms of service. And immediately they'll block all of IIT. They won't try to find out who did it. Okay. So in other words, look at this entire command out here, right? I basically started with cat, then went to cut, then I went to sort, unique, again sort. Okay, so all that I've done is used a bunch of different commands that already exist on a Unix system, in this case a Linux system, right? And I was able to achieve the entire thing without having to write even one line of Python code. Okay, instead I write one line of shell script, which is why you will find that, I mean, there are people who say that, oh, one line bash one-liners, so to say, are a big thing, right? Bash is the name of the shell, right? They are, of course, I mean, they are useful, clearly. They can also be overused. There are places where they just don't belong, right? One place, for example, so, let me try changing this slightly. And let's say that I want to do something a little different. See, this page is a PDF, but the next page, for example, is, something else. It is some PHP file. But after that, I realized that, there is something else where I'm actually maybe downloading an MP4. So let's say I want to find out how many MP4s are being downloaded, right? And what's the distribution on that? I could change this relatively easily. I first do a grep, okay? And this grep will search for the pattern .mp4. I need to put that backslash in front because dot otherwise will be interpreted in some other way. Okay. Now I don't want to get the first parameter. I think I want the 7th parameter. That's the actual file name, right? And I do the same thing out here. What happens? It basically tells me that, for example, this MP4 file was downloaded. I mean, this doesn't make sense, right? 25,000 times. Why would anyone download it 25,000 times? Some problem, most likely, right? Either they had a script that was trying to download, it was getting blocked, it was getting broken, their connection, something went wrong with it, but nobody in their right mind is going to try and download this so many times. If I see this though, I can then go further and try to find out from which IP did this happen. I can basically just grep for this particular file and then go in and start looking deeper into it, okay. So the point is, certain kinds of analysis like this becomes very easy because of this structure that I had, the pipeline, right? I was able to create it because of that one fundamental thing in the Unix philosophy. Programs consume data in some format, and they also produce data in the same format. What that means is I can take the output of one program and pipe it into another, okay. No, so that's the thing. I mean, see, this is useful for a one-off analysis, right? I just want to do this thing, I want to run through and try it, I can do it. But let's say that you want this to be running automatically, this is probably not the best way to do it. Why? Because look at what is actually happening out here, right? How many programs got run to get this one piece of data? I had to run cat, I had to run grep, one cut, sort, unique, and one more sort. Each of those, the shell has to actually invoke it as a separate program. The only thing it is doing is it starts all of them and then sort of pipes, okay, output coming from here, immediately send it to the next one, right? So it has to balance sort of so many different processes running in the background. It's perfect for one-off analysis. If you want to keep this running in the background, it's probably not the best way to do it. You will probably find that the Python script was actually faster, right, if you run it. If you really want to do this in real time on a large scale, even Python is not good because it's an interpreted language. It's not really the best way to do it. You can then go for some kind of a compiled log analysis program, either C or Go or something of that sort, okay. But what I want to sort of emphasize over here is this part of it, the fact that I can pipe things through, okay. Good question. In principle, yes, right. So these are all concurrently executing. So if you look at this, what you will find is that the moment I run this thing, all of these commands have activated. They've all been started off by the shell, okay. But let's say that the grep is searching through the files in order to find out what the MP4 is. As and when it generates some data, that immediately goes to cut, right. So cut immediately sees an input, right, and it does something with it and generates an output. Now, depending on whether your system was a multi-processor system or a single processor system, in either case, the operating system is multitasking, meaning that it's basically slicing time very finely, giving 10 milliseconds to one program, 10 milliseconds to the next, and so on, right, or some small amount of time. So the moment you have some output from grep, it will feed it into cut, it will then go look at cut, run it, and so on. But now look at sort. Sort doesn't work that way. sort needs the full input before it can start generating output. Okay, so the moment you hit sort, the unique and the sort after that are sort of stuck over there, are waiting. Okay, see, that's what I'm saying. These are not threads, these are full blown processes. So a thread is something else. A thread is when you have one program trying to create different threads, but which are all part of the same program. Whereas a process is, it could be completely unrelated things. So for example, I run Chrome over here, I run PDF annotator, I run this SSH client over here. Those are three different processes which have nothing to do with each other, and the operating system manages them, right? So from the operating system's point of view, you could think of them as three separate threads or three separate processes, whatever it is. So what's the problem with a process? There is a lot of overhead associated with it, right? I have to create some memory, I have to copy the program over there, I have to then allocate time for it in the overall scheduling of the operating system, right? So what's that? Yeah, you will have a memory overhead associated with it. Okay. Now all of that happens at the operating system level. If you are doing a thread, then it doesn't happen at the OS level, it happens directly at the thread level. That is to say, some other runtime has to be there which will manage different threads, right? But these are not threads, these are separate processes. They are more heavy than having threads. But on the other hand, because of the way they are created, they can make use of the multiple cores that are available in the system more naturally. Okay. Alright, so like I said, this pipeline, in other words, gives you an idea of what is possible in when you have different tasks to be performed, right? So what are these tasks? So here I had a grep which was just taking the data and looking for something in it. Okay, I had a cut which was just selecting out part of the data. I had sort which was taking a block of data, doing something with it and again generating an output. Unique which is trying to collapse some parts of the data together and so on. Okay. Now that leads me ultimately to the second part of the topic that I wanted, right, which, like I said, given my background, I am an electrical engineer. Okay. So what I have is, I am going to talk a little bit about communication systems. You don't need to know any communications over here. If you have done a course on signal processing, that would help, but again, like I said, it's not absolutely essential. Okay. But let's say that you are talking about something like audio. Okay. Now those of you who have done a course on signal processing might have seen pictures like this. What is this picture trying to show? It's basically saying that this horizontal axis is time, right? And each of these values, these blue dots that you see over here, are, let's say I have a microphone pinned to my shirt at this point, right? What is that microphone doing? It's picking up my voice and converting it into a electrical signal. Okay, it's probably a voltage somewhere which is then going into this unit out here, right, which is most likely converting it into a digital signal. Okay, at some point either here or in the studio out there, it's being converted into a digital signal. That is sampling. That process of converting into numbers is sampling. Okay, so each of these points over here, in other words, is a sample of the data. Okay, and they are actually converted into numbers that can be stored inside a computer, right? So after all, a real voltage is not a number, it's some physical value, right? So what I do is I compare it against other voltages and finally associate a number with it. If I say 1.3 volts, that may not be the number, 1.3 may not be the number that's actually coming out of this analog to digital converter. It will generate some number which, when you put an appropriate scaling factor, actually means 1.3 volts. Okay. So this sampling is used all the time, right? Sampling basically is how I can take a real world signal and convert it into something that can be stored on a computer, right? So when you have an MP3 audio that you are listening to, what was the process that went through it? It basically got picked up from a microphone, got converted into digital data, went through a whole bunch of different processing stages, right? Some filtering, some compression, various other things, and finally got stored as a file somewhere. And then you go and request it, it sends you the MP3 file and you can stream it to your computer or your phone and play it. Okay. Now, one of the most fundamental operations in this kind of signal processing is what looks like this, right? It's called a filter. Okay. So, what does a filter do? The simplest kind of filter that you can think of is, I have these numbers that are coming in one by one, just start averaging them together. Okay. So, take a, let's say, a running average of the past 3 or 4 or 10 samples, right? What do you expect the average? Let's say that I had a signal which looks, something very noisy like this. What do you think will happen if I start averaging it? I should expect to see something which looks a little smoother. Okay. So, that's one of the kinds of things that can be done with filtering. Another thing that you could do is probably say, look, I don't care about averaging, but I want to find out some particular frequency and see whether there was some content out there, right? Was it a doorbell that was ringing? Because I know the frequency corresponding to a doorbell. Did somebody whistle? Because I know what the frequency of a whistle sounds like. Okay, all of that are different kinds of signal processing that you can do. Now, the point is, look at what a filter looks like, right? It is taking in data in a certain format, which is a sequence of numbers, and giving out data in the same format, another sequence of numbers, right? Sounds familiar? This is exactly what a Unix pipeline was also trying to do, okay? So, if you come from this background, you can actually start to think of those Unix commands as filters. What are they doing? They are basically trying to transform your data in certain ways, okay? It could be smoothing it out, it could be like combining things together, it could be picking out one part of the signal, right, or the data, whatever it is that you have, right. So, the filters, in other words, naturally align with what you have in terms of the internal implementation. Okay. So, now, thanks. So, this is a sort of more complicated picture, I am going to skip through it because, the reason I put this up here is just to show you what an actual large communication system looks like, right. Literally what's going to happen over here is you will have samples coming in from an A to D converter, right, and then going through many such filters. There is one part whose job is just to pick out some property of the signal, where is it starting. There is something else which is correlating against another known signal. What is correlation? A kind of filtering. There is something else that happens over here. There is something called a transform, a Fourier transform, right. There is some other synchronization. All of these, what are they doing? They're just basically sort of taking the sequence of data in, doing something with it and giving a sequence of data out, which means that I can finally create this chain out here, which finally gives me data, bits at the other end, okay. A pipeline, exactly like what, structurally exactly like what a Unix pipeline also looks like, but operating at a very different level. This is literally operating at individual bits as part of a communication system, okay. Now, I'll probably stop in another few minutes just for a short break, but before that, there is one aspect that comes out as a result of looking at it this way, which I think is useful to know, okay, which is basically, let me use this to illustrate. I am going to create some kind of an arbitrary pipeline of things, okay. So, don't ask me what these ABC things are that I am drawing out here. They are just some computations or processes, right, and they are behaving the same way. They basically take in certain data in some format, process them, generate output. So, A does that, it takes some input, does something, generates output. B does that, it takes whatever A gave it, does something, generates output, blah 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 blah, okay. Now, let's start associating a certain running time with each of these things, okay. So, I am going to say that A takes, let's say, 10 seconds to process each chunk of data that it receives, okay. I don't know what A is doing, so let me even leave that word second out of the picture, because I don't care what time unit it is. Normally, I would have said nanoseconds because I teach this in the context of a hardware course. Over here, nanoseconds doesn't make sense, but neither does seconds. So, just 10 time units, I don't care what, okay. What about B? Let's say that B takes only 5. In other words, for each piece of data that it gets, it does something in 5 time units and generates an output, okay. C takes 20, D takes, let's say, 15, and E takes 10 again, okay. So, now what this straight away tells you is, if I put some data in here, right, how long is it going to take for me to get the output, right? It will be 10 plus 5 15 plus 20 35 plus 15 is 50 and then 60, right, at 60, right. So this is what is called the latency, the actual time required in order to generate the final output data. Now you might have heard the latency also in the context of something like a web application, right? Why? Because ultimately I am going and making a request, let's say to Amazon or something of that sort, right? I am trying to load their page. I sit over there waiting, and after a certain amount of time, suddenly the data comes up over here. That time to first byte, the time to the first response that I am seeing is my latency. Okay, but the interesting thing here is, now look at it, because of the pipeline, do I really need to wait for another 60 time units before getting the second data? Not necessary. Okay, so how does that work? Let's take a look at it, right? What I'm going to say is, I'm going to draw this A, B, C, D, E, F out here, right, on this axis, and say that first A executes, it takes 10 units of time, then B starts, it finishes in 5, okay. C takes over immediately after that and takes 20, okay. D then starts over there and takes another 15, and E then takes 10, right, there is no F, right. So in other words, this total latency was 60. But let's look at the next piece of data that I have, right. When can A start operating next? It can actually, immediately start doing something, right. It basically does something out here and generates the next piece of data, okay. After that B starts, and once again it only depends on this, which means that 5 time units after this B is ready. Now what about C? That's where the problem comes, right, because even though B has finished its work, C is not ready to accept the next data. So C can operate either when this finishes or when this finishes, the maximum of the two, okay. And what ends up happening is, it then takes both of those and runs from here, okay. So the second sort of iteration of C happens here. What about D? Same story, it has to be the max of these two, right, and therefore D starts from here and runs for another 15, right. Similarly, E also gets affected by this and finally runs from here for 10, okay. Now let's look at when this second data actually finished, right. If I look at the time over here, this is 10, this is 15, this is 35, right, which means that now this finishes at 55, okay, the second one, and this is plus 15, so 70, and this finishes at time 80, okay. Why do you see this? In other words, if I continue, I put in one more parameter out here, I'll find that the same thing happens, right. This next one also sort of needs to follow the same kind of pattern, and I can say for sure that this is going to finish at 100, okay. Why? Right, you end up having a bottleneck, right. So in other words, this one becomes the bottleneck or the rate limiting factor, right. So the fact that C over there is taking a certain amount of time is ultimately going to slow down your entire pipeline. It doesn't matter that you had like really fast ways of doing all the other things. At some point you are going to hit this slow stage, and that determines the throughput of your system, okay. So once in 20 time units, this is basically the what we call the throughput of the system, okay. So the throughput basically says, okay, look, it might have a high latency, it has 60 time units to generate one piece of data, but every 20 time units after that I will get new outputs, okay. This analysis is important, like I said, in hardware of course it's crucial. This is exactly what we talk about when we talk about pipelining hardware, okay. And even if you are not a hardware or an electrical engineer, you have probably heard of Intel processors with a 20 stage pipeline and how they run at like 2 gigahertz and so on. This is pretty much what's happening, right. what is there inside a processor? There are multiple units. There is something which is fetching data from memory, there is something which is actually performing a computation, there is something which is writing or reading from a register file. All of those units are taking time. They fall into a similar kind of pipeline. One of those stages is the limiting factor that determines the speed at which the system can run. Okay. So, this, in other words, this analysis holds exactly even for the Unix pipeline. If I actually had some kind of a scenario where there was one unit out there which was the bottleneck, I could actually say, okay, this is the best throughput that I can expect to see, right. In the example I showed you, it's a bit worse than that, because what ends up happening is sort is sort of a complete blocking thing, right. Everything has to come in there before it can sort. But let's say that you are willing to sort only like groups of data at a time, right, then you might have been able to actually have some kind of a thing where there are multiple iterations running through this. Okay. So, where we left off was that you know what determines the bottleneck or the throughput of a pipeline. Okay. Now, a pipeline that I have shown this way seems to be a very sort of simple limiting case, right. I mean, I always have like a single input, single output kind of a system. Is that necessarily the case? And the answer is no, right. I could go beyond that. I could, for example, build up a system where I have A feeding into B, and then B suddenly branches out, right, and then D maybe goes through a little bit more computation, but then at some point both of these sort of feed back into a single system and then they combine, right. Now, how do you analyze a system like this? You can do something very similar, right. How do you first of all build such a system, right, and over here the shell pipeline starts breaking down, right. It's not easy to do it. There are ways. For example, there is one command called T whose job is more or less to do this, right. It basically splits data into two, right. So, unlike cat, which basically takes the input and directly puts it onto standard output, T takes it and sort of does a T junction, right. It basically writes one into a file and the other one into standard output. You could do some fancy redirection and say that, you know, instead of writing into a file, I will then write it into another shell, a subshell or something else, okay. But it starts getting too complicated because the shell, the Unix shell wasn't really meant for that kind of behavior beyond a point. But in terms of hardware, we do that all the time. In fact, you have to, because there are very often scenarios where you are doing like, you know, fairly different kinds of processing on the same data and you need to put the results together, okay. Now, what that means is that, but if you look at this picture, right, is this hardware, are these A, B, C, D, E, F, you know, hardware modules, are they a set of software programs, are they functions somewhere else? By looking at this picture, you can't say, and that's intentional, right, because at some level all of these things are what we would just call tasks, okay, and this essentially falls under what is called the analysis of task dependencies, right, which in turn leads to another aspect, which when you look closely at this, you will realize that, look at these two tasks C and D, right, do they have any dependency on each other, right. One thing I can say for sure is, look, B depends on A, right. What I mean by saying B depends on A is that until A finishes or A does something, B cannot proceed, right. Similarly, C depends on B, D depends on B, because both of them are taking inputs from B. But does C depend on D? There is nothing to indicate that, okay. So, effectively, in other words, I could probably say that these two tasks are parallel or could be potentially run in parallel, okay. That does not mean necessarily that they actually run in parallel, it is just potential, right. I can do it in parallel, I do not care about the order in which I do C and D. As long as both of them happen after B, that is all that I care about, okay. Similarly, C and E are also task parallel, right. I do not care about the order in which I do C and E. What I do care about is E should happen only after D. As long as that is taken care of, whether I do D, E, C, C, D, E, D, C, E, right, none of those matter, Okay, so this kind of dependencies and the parallelism in tasks can be captured like this. Okay, what ultimately happens is that this sort of leads us into a fairly complex level of analysis of this entire thing, right, which ultimately comes down to this problem of task scheduling, right. So what is task scheduling? Basically what you have is you have a set of tasks, some work that needs to be done. Those tasks have certain dependencies between each other. Okay, you need to make sure that all the dependencies are satisfied, but at the same time all of these tasks are somehow executed in some way, right, I mean with some cost. So either you want it to be the minimum amount of total time, or you want the tasks to be sort of put on processors that are less expensive, or you want them to consume less power, right. So there could be many different cost criteria that you are dealing with, but the problem itself says that look, I have certain dependencies, the dependencies need to be satisfied. Subject to that, in what order should I actually go about executing them? So unlike a simple pipeline where things are relatively straightforward, right, I need to do things in a specific order, but even there I do have one level of flexibility, right. What is that? I could do multiple iterations of A, accumulate a lot of data, and then start on B. Okay, that's perfectly valid. So for example, even in the Unix pipeline that I showed, the cut, I could run cut through from beginning to end, right, generate the entire first column of data before I start doing the sort. Okay, that's a valid way of doing it. I don't necessarily need to sort of pick out each and every data, or rather the grep, I could have run it through to completion before I pipe it into cut. Okay, that would have been perfectly fine and acceptable, right. So in which order you do it is something that is actually left open to you, right. This entire area of task scheduling has been approached from many different directions, right. So you will find that in the computer science domain, people look at it from operating systems, just generally from the point of view of algorithmic complexity. How hard is it to solve this problem? And it turns out it is very hard. Okay, this falls in a class of problems that are called the NP hard problems, which essentially don't have any good known efficient solutions. Okay, but it's not just in computer science. Like I said, I'm from a sort of electrical engineering, but you could call it computer engineering direction that I am looking at this. Once again, the same kind of problems related to hardware implementation. In some sense, a more or less unrelated place where you find this is in operations research. So we have a management department, for example, where they do a lot of research on this. Why? It's the same kind of thing, right? I mean, you look at tasks, right? Even if you're trying to build a flyover somewhere, ultimately there are a set of tasks associated with that. You need to acquire land, you need to then clean up the area that is there, make sure that all the surrounding things have been moved away, then start digging up, lay the foundations. All of those are tasks that have dependencies, and in some cases there could be parallelism as well. You could be sort of digging on multiple parts of it at the same time, or while you are digging you could also be sort of preparing prefabricated structures for the next stage, right. So there are different ways in which you can look at it from a management point of view as well. Okay, so in the most general case, this becomes what's called a directed graph, right. And this whole area of graph theory and how you analyze graphs and do a lot of different algorithms on graphs starts to play a role in this context. Okay, all right. So now that's the hardware side of things taken care of. Let's get back to data science, right, which is sort of problem 3 that I had in mind. Okay, and what I'm going to do over here is look at a simple neural network. So what does a neural network do? I am sort of going to assume that you are broadly familiar with the core concepts of what neural networks are, right, in the sense that a neural network at some level is taking in some data. There are some inputs that are fed into it and they go through layers, right. So what does each layer do? A layer is doing some kind of computation on the data. Most of the time that computation would be something like some multiply, add, some matrix vector multiplications or matrix multiplications, something like that, right. You might also be familiar with terms like convolutional layers and dense layers or fully connected layers and so on, right? Right now, I'm going to assume that layers exist. What exactly do they do? I don't care. Okay, they are doing some kind of computation. That's all that really matters to me. Okay, but the thing is, how do you actually go about constructing a network of this sort, right? And what does that have to do with what we have been discussing so far? Okay, so as an example of that, we can actually go back and look once more at So what I've got over here is, just this is some Python code that I have taken directly from the website of the Keras API, right? So how many of you have heard of Keras? Good, a reasonable number, okay. So what is Keras? It's basically a Python library, right, which allows you to interface with TensorFlow, which is once again a set of routines that is mostly developed by Google, which allows you to sort of model neural networks, okay. And this particular code was the example that is used in order to solve what's called the hello world problem of neural networks, right. It's called MNIST. It basically says, okay, how do I recognize handwritten digits, okay. The idea over here is you have a number of small images, right. Each image is just a 28 pixel cross 28 pixel, so 28 by 28 small image, black and white, okay, which contains, or maybe grayscale, I'm not sure, yeah, I think grayscale, which basically indicates is a scan of what somebody has written within a box, okay, a number that has been written within a box, okay. And what you have over there is you are then trying to see whether the computer can automatically classify this as a digit from 0 to 9. So it turns out to be a relatively simple and easy starting problem, right. So a lot of people have code for that, and it's a good sort of starting point to understand how to use these libraries. So what I did was I just sort of picked out the data from there. The interesting part as far as I am concerned is this part over here where they construct a model, okay. And what exactly is the model doing? It's basically saying you have an input which then goes through several layers, right. So I have a layer.conv2d, I have a layer.maxpool, another layer convolution, pooling, flatten, whatever dropout is, and dense, okay. If I look at it from the point of view of the architecture, I would see something like this. I have an image, right, which is then fed into a convolutional layer, right, and the convolutional layer would basically be some kind of, it's usually denoted as something like this, right, where it basically says that I have my input image, which is then going to sort of, rather I take a small block out here, filter it against this and generate an output, okay. So the output of the convolutional layer is once again another image, right, which then needs to be sort of downsampled, reduced in size, something, right. So this would be a convolutional layer. This would use something called a pooling layer that reduces the size. Then I have another convolutional layer, right. Again I have some pooling. Then I have something called a fully connected layer, right. And over here in the fully connected layer, what actually happens is that this is almost like a huge matrix product, okay. Bottom line is each of these involves some computations, right. Once again I can start thinking of them as I have an image, I have a task which is a two-dimensional convolution, I have another two-dimensional convolution, and then I have a dense layer and I have output, right. Starts to look familiar, the same structure again, right. You have a pipeline of things that are coming through. And if you look at it, that's exactly what's happening out here, right. You look at the model that is being used by Keras, it basically says this is a sequential model, What does a sequential mean? It means that it is taking inputs of a certain size, passing that input, right? So all that it is doing is it's basically taking all of these layers and feeding the output of one into the next. Okay, so in other words, it's just directly creating a pipeline out of the things that you have provided to it out here. Okay, input goes into a conv2d, that goes into a max pool, again convolution, pooling, flatten, dropout and dense, and finally you get an output over here. Okay, and it turns out that that's finally you can actually print out what the model looks like and so on, right? But what is more interesting for us is to sort of see, okay, can we sort of look at this? And this is once again an example from the Keras libraries, which says that for code which looks like this, right, I have some dense layer, then I have that input, then I have this thing. I'm basically going to end up with a pipeline which looks like what's shown on the right. Okay. One interesting thing that I want you to observe over here is actually what is happening to this, right? I have certain inputs, and then I'm saying I'm going to take this x, apply the function dense on it, and I create an output x. Okay. Now look at this second statement out here. What it is saying is, it is saying layers dot dense, something of this sort, and then suddenly I have these parentheses out here and x applied to it. So in other words, this layers dot dense, this entire thing itself is a function call, right? Because after all, layers dot dense is, it looks like a function call, right? It takes parameters and it's doing something, but what it's returning is itself a function. Okay, so in other words, this is a function which is then being applied to x. What it returns in turn is actually also a function. Okay, and why am I sort of making a big deal out of this? We'll get to that later, right? Because that's sort of the point of where we are going with all of this. Anyway, the interesting thing about Keras is it also has something else called the functional API, right? Not the sequential API. In the functional API, what it says is, for example, you can directly create multiple different inputs. You can create these different sort of layers one after the other, put everything together, and what is interesting is your graph could look like this. Okay, it's no longer a sequential graph, it's no longer a pipeline, it's more like a directed graph. Okay, it's still directed, that is important, because there is a notion of input coming in from here and finally output at this end, right? But there are, for example, multiple inputs and multiple outputs, and in between there's a whole bunch of other processing that's happening as well. Okay, Keras, for example, allows you to build something of this sort. Okay, so the same kind of notion, once again, if I now take this network which has been designed by someone and I start asking the question, how fast can it run, right? Because why would I be using this finally? Let's say that I have got an image processing problem that is able to recognize faces. So what does Google Photos or Facebook, for example, do, right? You upload all your, you take all the pictures, you upload it over there, and they have got like this huge amount of data that they are having fun with, right? I mean, they are training their facial recognition algorithms on that, because every now and then it suddenly pops up and asks, is this you? It's like, okay, they have done a great job of getting like every single face on earth over there, right? But it's then training away on that. The point is the sheer volume of data, right? I mean, how many of you took selfies today and uploaded it to Google Cloud, right? More data for Google to work with. It has to process all of that, and it has to sort of figure out where are the faces and match them against its databases, right? Now, that means a huge amount of computing power that they need to implement, right? And also, how fast can you do it given the sheer volume of data being thrown at it? Yeah, so I don't think Google checks against the entire database of faces. I think they do it more intelligently, which is that if they know that you are taking a photo, it's first going to match against you. Then it sort of figures out who are the ones who are common in your subset. It's probably almost creating something which is sort of specialized for each person. I mean, because they can't do it otherwise. I mean, with like a few billion images, you can't sort of do a matching against everything. But whatever, the point is, even with only a single person's data, the amount of computation involved is huge, right? So how do you deal with that? You have to have something where the processing that you are doing sort of gets distributed nicely across a set of computers. This allows you to do that. You can do the analysis, right? What is the computation required at each of these layers? Where should they go? Where do I have parallelism? How can I parallelize some parts of it? All of that comes out from this analysis, this structure that you have out here. Okay. Now, once again, the important thing that you need to recognize over here is, remember the Unix philosophy that is now applying to each of these layers as well. Each and every one of these is a function. It takes an input in a certain format, it gives out input in a similar format, which means that its output can be fed into another function. Okay. This idea of composing functions one after another, you take the output of one function, feed it into another, feed it into another, feed it into another, is very powerful, and that is sort of what I meant by the power of pipelines to start with. Okay. Now, yeah, sorry, yeah. No, so what I mean actually is that in Python, for example, see, in C, right, you can declare a variable to be of certain types. I can declare it as an int, a char, float, right? So those are sort of the core data types available in C. Okay, but in Python, I can actually return a function itself, the name of a function, as the return value of a function. So a function, in other words, can return a function. Okay, and that is what is sort of happening out here. If I look at this, right, this layers.dense is a function call. What is it returning? It's returning a function. That is what is being applied to this x. And interestingly, it's not actually being applied to x. Finally, it is being composed on x. It is also returning a function. So x, in other words, at this point is not a value, it's not an integer, it's not a float, it is a function. Okay. So this idea of functions as first class objects that can actually be passed around between different parts of a computation is what is sort of at the core of this whole idea of functional programming. Okay, and is what enables a lot of these ideas, or rather, it's not that it fundamentally enables it, because I can do this even in C in principle, right? It's not that, because even though C is sort of as close to a definition of an imperative language as I can think of, I can do this kind of programming even in a language like C. So it's more how you think about the programming rather than which language you are using. Okay. Yeah. So, I mean, that's a good question. If it's not acyclic, there has to be some way by which I can break the cycle. I need to know at which point to start and where it ends. Okay. So, for example, in actual digital circuits, you have cycles, but those cycles are usually broken by what are called the flip-flops, the registers that actually hold the data. In the same way, when you have a graph of this sort, you might have feedback, right? So you might, for example, have something which does an image recognition, and at the end of it, the recognized value is fed back to improve the training. But then I need to have that some sort of distinction between what came as the input versus what is being fed back. So I can break the cycle at that point. And as far as the analysis of throughput and all is concerned, I will always do it on the acyclic graphs. Okay. Alright, so this sort of leads me to the last part, right? The architecture of the web platform. And what exactly do I mean over here, right? Look at where we are starting from, right? We started off with this image of you sitting at a computer, right? You have the client, which is then making requests through a cloud going to a server, right? And what exactly does the server consist of, right? This server is not sort of just one machine sitting somewhere in a data center. Usually what you will find is that this is actually something called a load balancer. What does a load balancer do? It's a program running somewhere on a machine whose only job is to basically sit there listening for network requests, and as and when it gets a request, what does it do? It forwards that request to someone else to answer. Okay. So usually what it will do is it will end up sending out the request to one out of many so-called front-end servers, right? What are these front-end servers? They are the ones who actually take the HTTP request. So if you are writing a Python Flask application, for example, this will be the one which is actually running the app over there for you, right? It knows, in other words, that if it gets an HTTP request, where to look for the answer. So the front end is also doing something similar, right? It's sitting over there waiting for a request, and as and when it gets a request, it does something and it has to eventually come back with a response. Okay. Now this front end, for example, might be just dealing with static files. What do I mean by static files? It could be JavaScript, it could be CSS, it could be plain HTML files, it could be PDF files, MP4, but something which doesn't need any computation. It's just there on the file system, pick it up and throw it back, okay? Whereas this might be something which is actually, doing some business logic, and more importantly is also interacting with a database, okay? What is the database doing? It receives requests from the business logic, creates a new entry or like fetches data from the database, sends it back, okay? And the database, in other words, is just doing its job. That is to say, whenever it receives a request for doing something, it puts the data over there. If it has something else, it basically, if it's like delete something, it deletes and then sends back a response. If it's change something, change and send back a response, and so on, okay? And this business logic ideally is also something which is just taking a request from the front end, deciding what to do with it, sending it to the database backend, and then forwarding, the response all the way back, okay? So you can see that even at the hardware level, or rather, this is not actually hardware level, these are tasks. I can think of load balancer as a task, static file server as a task, business logic as a task, database as a task, okay? All of these could be running on the same server, or they could be distributed across multiple servers. The moment I have defined my tasks in this way, it means that now I can think of spreading it out, okay? In fact, right, so what happens ultimately over here is, if I have this whole thing being broken up into a large number of tasks, that's where you might have heard of these terms called microservices and so on, right? Each task does only one thing, right, but does it well, effectively. And by sort of coordinating between a large number of such different tasks, which may be running on the same machine or on multiple different machines, it doesn't really matter which, I can get high performance out of the entire system, okay? And where did all this come from? If you think about it, right, ultimately, like, so, that was sort of what I wanted to say about the architecture of the web platform. But now if I want to tie all of these things together, right, I want to emphasize this one part, which is this notion of functions, okay? Effectively, everything that we have over here is y is equal to f of x. X is a request and f of x is whatever is the response for that, okay? In the case of a Unix pipeline, x is a request, f is the cut function, the response is the first column of data, okay? F is the grep function, the response is whichever lines matched against that expression, okay? In the case of web architecture, right, x is an actual HTTP request, f could be that it picks up a Jinja template somewhere, renders it, gives you back HTML, okay? Now, the important thing over here is that there is also a notion of something called a pure function and something called a side effect, okay? A pure function is one where every time I call the function with the same data, I will always get the same response, okay? If I define my function as f of x equals x squared, right, it doesn't matter how many times I call it, if x is equal to 3, I will always get the result 9, okay? But I could potentially have something which basically says, what is this f, save x to some storage and return x plus 1, or x plus, or rather, read something from storage compute, return this value x plus data from storage, right. So supposing I get something t is equal to this x plus t, and write x plus t back to storage. Okay, what have I done over here? I have basically said that every time I call f of x, the answer is going to change, right, because the first time that I call, let's say f of 1, okay, what it will do is I have this t out here, right, which will take the value 1, and I will also get back an answer 1. But the next time that I call f of 1, I will take this 1, add it to x, and I will return 2, and I will also write t is equal to 2. In other words, this first f of 1 and the second f of 1 can give me different answers. Okay. Now that is essentially something called the internal state of the system. Okay, that by itself may not be a problem. The problem happens when I am also trying to sort of alter something which is there, like for example, if I want to print something on the screen, or if I want to save something into a database, or if I want to go and send an email. All of those are things which alter the behavior of the function. Every time I call them, the behavior is going to be a little bit different. Okay. Now, if I had a function where I can guarantee that every time I call it, I will get back exactly the same result if my input was the same, that has some very nice properties. One of them is testing such a function is relatively easy, right. I know that I can basically give it some specific input parameters and say, okay, this is it. For this input, it should give this output. I don't need to know what the rest of the system looks like. I don't need to create a dummy database. I don't need to sort of have any other mock test set up around it. I can just basically test the function by itself. Okay. So effectively, in other words, what would happen is the testability would improve. The second thing is, if I know that for a given input, I am always going to get the same output, what does that imply in terms of scalability? That is to say, can I now run this anywhere? Can I run it on a different computer? Can I run it on a different server somewhere else? Yeah, because I know that no matter where I run it, I'll get the same answer. Okay, so scalability also goes exactly the same way, right? So these two properties are sort of the key to how you should be thinking if you are looking at something which can really try to start scaling up. Okay. Because if you have a very complex function that is being, or a complex web service that is being implemented that depends on many different things, scaling that becomes hard. But if your core functions are sort of limited and you say that, look, all my logic, I will try and break it down so that as much as possible is just a transformation from input to output, those parts can scale beautifully. Okay. So you have probably, some of you might have heard this term serverless. This is what serverless is, right? Why does serverless come into the picture? Because I don't really need to have a specific server. I just have a function that has been defined in such a way that anytime I run it, it is just going to perform the computation and give me back the result. It can basically spin up at a moment's notice somewhere, anywhere, somewhere on the cloud and give me an answer. Okay. And things like Google App Engine really sort of scale beautifully if you have your functions sort of cleanly defined like this. Okay. So in some sense that pretty much brings me to the end of the topics that I had in mind. So if it is, in other words, see, okay, when you say multiple outputs, what do you mean by multiple outputs? I mean, yeah. Okay, but see, as far as I am concerned, I don't consider that as multiple outputs. I'll group plus or minus 3, plus 3, minus 3 together as one object, which is being returned by the function, one tuple, if you want to call it that in Python, right? Or you call it a struct or whatever it is. I would say that that's still one return value. Yeah, I would still consider it as one output, right? What about the modulus function? Why would that be different? That is okay, I don't care, right? I'm not trying to invert the function here. I only care that for this input it gives me a fixed output, which means that I can implement it anywhere and it would give me the same output, right? So any function that way, I mean, the problem comes when you have a function which each time you call it could give you different results, right? Now, I need to be a bit more clear on that. Even that may be okay. You could have a scenario where, let's say, a random number generator, for example, right? Every time you call a random number generator, you actually get a different result, right? The only thing that doesn't work in that case is that you will get exactly repeatable results no matter where you run it, but the overall performance would remain exactly the same. Barcode. Huh. Huh. Barcode, why should it give you a random number? Huh. Right. See, that may not be necessarily random. I mean, so okay, that's a slightly different scenario. That is, I mean, there are two ways of handling it. Okay, so just to be clear, I guess the problem that you are saying is you want to assign, let's say, a barcode to every desk over here so that it can be uniquely identified, right? Now, there are two ways of doing it. One is, like you said, every time I go to the desk, it generates a new random number. And now I'm hoping that it never repeats the same random number, right? So that's one way of doing it, yes. With sufficiently large scale of randomness, I should find that, I never repeat random numbers across different desks and so on. But what is the correct way of doing it is probably slightly different, which is that you actually generate a unique ID each time. In which case, I need to store the unique ID in a database somewhere, right? And so, see, that comes into this problem of the side effects. You actually have to generate a side effect. Some data somewhere else which has nothing to do with your function has to get modified. And you have to keep track of that when you are generating the next output over here, right? When you have side effects, you can run into problems. An example of a side effect is similar to what you said, right? Let's say you are developing an application where you can do the CRUD operations, create, read, update, delete. Every time you create, right, the database is getting updated. Now, think of this as being, you say that, oh, this is serverless and I'm going to have it in all different functions in different places. It's not so easy anymore because each of those serverless things that are running finally needs to update the same database. Okay, that becomes the bottleneck. You can't just parallelize over here because you will have a bottleneck somewhere else. So that's the question. If you find that, you can actually, so you're effectively, in other words, everything that you are saying, if you want to optimize, if you find that this is becoming a bottleneck, what do you do with the database? You create multiple copies, read-only copies of the database. You are modifying the task graph, right? So that's basically it. I mean, the best way of sort of looking at all of these applications is to say, okay, look, I have a performance problem. How do I improve it? Can I parallelize somewhere else? Sometimes you might find that just by looking at the task graph, you can actually get your job done. In other cases, you might find that you need to modify the task graph. But either way, this way of looking at it, right, that each of those tasks is a self-contained function and that there are dependencies between the tasks, that really helps to sort of visualize what is happening and to get the entire thing working in the way that you want. Okay. Now, why did I bring in this whole notion of functions? Because there are certain languages, right, which fundamentally have better support for so-called functional programming, right? Python has what is called the lambda operator, right? So you can define something called an anonymous function in Python, right? You can literally say lambda x colon x equal to x plus or return x plus 2 or something like that, which without having to define a new function is implicitly there and can be used in specific places, right? That word lambda is there for a reason, okay? Because this whole sort of notion of function composition was studied in great detail as part of the so-called lambda calculus, right? Which was originally proposed, I think, as part of Alonzo Church. This is like from the 1930s or so, okay? That lambda calculus in turn was the sort of core idea behind a programming language like Lisp, right? Lisp is one of those weird languages. It has, to me, it's one of the most irritating syntax possible, right? I can't stand to look at it, but it has a reason, right? When you look at it and you start understanding it, that's when you see that the syntax is so simple that it cannot be simplified any further. Just those parentheses that you have over there allows it to represent any sort of task graph implicitly, right? So a program, you are literally just creating the task graph for the program as you go forward, okay, when you are writing in Lisp. It means that of course you need to change the way you think, but it helps, right? Nowadays, of course, there's one language which is very popular in functional, which is Haskell, okay, you might have heard of that. And in fact, there is this company called Hasura, which is an Indian company, right? Indian, at least the founders are from here, which has had a lot of success in terms of building sort of good API servers and so on with Haskell, right? Once again, the same thing, they are basically relying on this fact that you have this functional core, which means that certain things can be expressed very nicely with this language, okay? So, the bottom line, okay, just to sort of conclude, what I would say is this: why did I bring all of this in? Because I want you to sort of think about, is this a useful way to apply to the way that you think about problems, right? Any kind of problem, not just in the domain. See, the reason why I brought in these 4 different things, right? One is the Unix shell pipeline, the other is hardware design, then we had like neural networks, and finally web applications, right? In some sense, they are fairly distinct kinds of areas to look at, but they have this kind of commonality, most importantly because of the way that you sort of think about the problem, okay? And this way of thinking can enable you to sort of bring in a lot of extra analysis and optimization which may not have been possible earlier, okay? And hopefully it will also encourage you to learn some other programming language or some other technique, right? Even if you don't go ahead and learn Lisp or Haskell at this point, a little knowledge of functional programming will tell you a lot about why it is useful. And then you might find that you actually start thinking along those lines, and your overall programming skills also improve, right? JavaScript, for example, is one of those weird languages. There are a lot of people who absolutely hate JavaScript. There are a lot of people who like it because it is very useful for building apps. I actually like it for a different reason. I think it's a very practical language. It has a nice mix of what is functional, right, and some factors that can be done very nicely. The problem with it is you can also write very bad JavaScript code, okay? So that's the thing. Don't think that a particular language or a particular programming style by itself will solve all your problems, but thinking in a certain way can sort of make certain kinds of problems more sort of tractable when you look at it, okay? Alright, so that's basically it from my side. If there are any questions, of course, happy to continue for as long as we need. Otherwise, we can stop. Yeah. Yeah, see, so actually state is something slightly different. I mean, if you look at even something like Vue or React or whatever it is, right, the sort of core idea of those Vue in fact is this thing, right, UI is equal to f of state, right. This is one slide that I put up in fact in the AppDev2 course also, right. And what does that mean? It basically means that you now have this way by which the way that a program is written can be composed of multiple different functions, right. And one thing in fact that I did not mention over here is from the point of view of application development, there is a language called Elm, right, which is not the most popular language for developing web applications, but this thing called the Elm architecture, right, which is the core idea of what Elm does, has actually become very popular. And even if you go and look at some libraries for React and for Vue and so on, the state management libraries, they talk about how they build on the Elm architecture, right. Now the core idea behind it is again something very simple. It basically says that you have a view, right, and you have some kind of a model, and you have messages being passed between them, right. And Elm is a heavily functional language. It basically has this notion of everything being just functions that are transforming. So if you think about it, that's what is happening. The view is basically providing you with certain inputs. They are being transformed with information about the state into something which needs to come back to the view. Okay, so thinking in those terms allows you to sort of do a lot of this cleaning up the way that you write the code. So whether or not you have state, in most cases what you will find is that this is a good way of thinking about the language. One thing, from a pure performance point of view, you need to keep in mind that at the end of the day, the processor that's sitting inside over here is an imperative system, meaning that it literally has an instruction set that tells it to load data, one word at a time, and it tells it when to add, when to subtract, when to multiply, when to store data, when to retrieve data. Each of those is a specific instruction. So it's imperative, no doubt about that, right? Which means that for raw performance, you might find that actually going back to imperative code is the right thing to do. But if you look at what is happening with, even something like Keras out here, right? You have all of this code. The good thing about Keras is there is then a compiler or even a runtime that can decide whether parts of this run on a GPU or a CPU or an FPGA, or how do I even split it across multiple CPUs, right? All of that can be done because you have written it at the higher functional level. Right, so it can actually get you like extremely good performance as well. Yeah.
We can make own browser better than anything in the world.
Depends on what you want your browser to do. In what sense do you mean better than anything in the world?
Like Chrome is a main browser, searching browser.
Yeah.
And anything browser in this world is not popular like a Chrome.
Well, yeah.
Better than Chrome for future.
I mean, okay, short answer I'll say is you can't, and I'll try to explain why. Okay, Chrome is where it is because of the number of years of experience behind it. Okay, now it started as, sit please, right? It started off as this thing called KHTML from the KDE project, right? So there was this component called KHTML which was there inside one browser which was written in the late 90s, right? At that time, which was the most popular browser? That was Netscape Navigator, which is now eventually it has become Firefox. Okay, but the problem with Netscape and the problem with KHTML was the majority of PCs used Windows, and Windows had the Internet Explorer browser. Now Microsoft wanted more people to use Windows. They started adding extra features to their browser. Said that, oh, this particular website, there were, I think luckily nowadays you probably don't see it too much, but there would be things like optimized for Internet Explorer, view at 1024x760, stuff like that. Okay. Now the problem is there would be people who would say, oh yeah, everybody coming here is on a Windows machine, so let's try and optimize for that. Because of their market share, they were able to do that. Now what happened was Apple at some point decided they wanted a better browser. They took KHTML and they built something on top of it called WebKit, okay, which is the core of the Safari browser even today. But that same WebKit was then sort of branched out as the core of Chrome. Okay, now which means that you are talking about more than 20 years of code which is underlying this stuff. The closest that you have to another browser with that kind of lineage and that kind of history behind it is Firefox. In fact, Firefox is even older, right? But of course, Firefox is also being significantly redone at this point. Now, why is that important, that so many years of this thing? Because if you look at what is required in order to make a browser which will be able to browse through 90% or 99% of websites today, there are so many corner cases that you need to take into account. How does it render CSS? How does it render JavaScript? Is it pixel accurate in terms of how it renders every single page that you have? Okay, passing all of those tests is bottom line is it's just a pain. There's really no benefit to it. You are not going to come up with a browser which is better in some ways than Chrome. Okay, what you could probably look at is a different direction, which is, can you sort of figure out why Chrome occupies so much memory and is so slow, and can you do something to make it faster, right? So if you, increasing efficiency, but it's like hard because the sheer volume of code that is in there that you need to modify is difficult to do. So see, there are certain things, I think they call it there are some names given to those tests, right? But if you write a new browser of your own, unless it passes those tests, people will probably say, look, it's not rendering so many websites correctly, right? So why would I use this thing, right? So that is why, I mean, if you want to write a browser, you should probably try it, but making it successful is a different story. I mean, Firefox is already struggling, even though they have actually a very good browser, but nobody uses it because everybody ends up using Chrome, right? This is not a technical problem. At this point, it's not, the reason why Chrome is the most popular browser is not purely for technical reasons. It is also a market position. They are the leader. Everybody has to comply with what they do. So it's sort of, you know, and they are good enough that people aren't going to sort of protest in a big way and walk away from it. But no, I'm looking at it the other way, that the individual components inside the pipeline should be functions, right? But the pipeline itself is a much more complicated beast. It could be a complete directed acyclic graph, which is, you know, the evaluation of that thing would be something which sort of goes from input to output, but it could be something that you couldn't predict by knowing any of the individual functions by themselves.
The pipeline can also be thought of as a function and can be used.
Yes, yes.
And when we go from top to bottom.
Yeah.
So the kind of operations that I perform in a function, is it that in order to evaluate the performance, probably somewhere underneath the stack, we have to translate that into a hardware instructions.
Yeah.
So how do we know that we are crossing that line, and we have to look at the way the compiler is actually translating the code, and that is hitting the performance, or
Yeah, no, I mean, there's no easy answer for that. I mean, the way that I would look at it would be something like this. Let's say that you are trying to create, I mean, even something like this, right? It's a Keras code which is running somewhere. Now, ultimately, to me as a hardware engineer, the way that I look at it is, if I have a CPU which is running at 1 gigahertz, it means that I can run 1 billion instructions per second. Now, what is an instruction? It could be an add operation, it could be a memory access operation, it could be a jump or branch operation, right? Or it could be some of the vector operations that are present inside the CPU as well. Okay. So ultimately, the question that I'm going to ask is, I have a certain amount of computational capability for the CPU. It can do 1 billion additions per second, let's say, or multiplications per second. How close am I to that? Right? So I would basically look at it as, is the CPU really being kept at high utilization? Okay. So usually what would happen on a Linux system, for example, is you can look at something like a top command, and it would tell you, is the CPU being used at high utilization? You might find that it is not. And the reason for that is probably that, you know, your program is using such a lot of memory that it's just fetching and writing data back and forth from memory and not really doing anything useful. It's just waiting for data. Or it might be writing to disk, and even the memory is not being utilized properly. Okay. So identifying where those bottlenecks are is ultimately, I mean, there's no sort of simple answer to that. It is unfortunately, it is one of those things which is not a good answer. It is only experience that can get you there, right? You try this out with different things. You sort of know that, okay, these are possible areas. So even as a starting point, you know what a CPU is doing, you know the kind of computations it's doing, and you start looking, is this really optimal? Could I do something better, and so on? Can I build on it? No. So let's say that a data scientist is trying to come up with a new architecture for a neural network, right? They are probably not thinking about efficiency at all. They are looking at recognition accuracy. How good is my network, right? Is it able to do face recognition perfectly? Is it able to sort of predict the correct class in each case? After that comes the hardware optimization, right? And there, okay, if I have things like this embedding and LSTMs and so on, I know that, I mean, the good thing is, when I use Keras, I can directly rely on TensorFlow as somebody else has done the job of writing a very good function for LSTM, right? Which means that if I can just use that function LSTM directly and hope that it will run very efficiently on my hardware, right? In some cases that works, in some others it may not work as well as required. You might find that your image sizes are too big or too small, they are not really making use of the hardware efficiently, and do a lot of optimizations on that.
At that point only we investigate and see
correct
where the slowdown is, and probably we end up writing our
or trying to see if you can break this function into some other way. Yes, but exactly, you're right. That's, yeah. Sorry, passwordless login? Yeah. Ah. Yeah. I mean, I don't think that will work. I'm not doing any of that stuff. I know. I mean, they might do all of that. They can't get rid of it altogether, right? Because see, if they say that every single image that is being captured has to be sent to their server to log in, that is a serious problem because it might mean that I'm in a phone without network connectivity. Are you telling me I can't access that phone? Right? So there will always be a fallback, which is a pin or something else which is there. But in most cases, there are also privacy issues, right? You don't want the photo to be sent over there each and every time. You want to be able to do the recognition on the phone. So Apple, for example, when you have an iPhone and you pick it up, it's doing the recognition completely there, right? Similarly, Windows Hello also does the recognition right on the machine. Passwordless logins are actually a slightly different story. I mean, what they are doing is they are coming up with multiple different things. It's not just image processing, it's not just face recognition, but they are looking at different ways by which they can get rid of passwords because traditionally passwords are a very weak link, right? You have a scenario where passwords leak. People share passwords or people can guess passwords, they use bad passwords. So they are trying to sort of get people out of the habit of using passwords. Either use your face or use a hardware token, a key of some kind, right? Or something else that, or the OTP kind of approach. All of those are different things, not just the face recognition alone. That leads to other problems that they would also need to solve. Sorry? So there are many different ways of storing images, right? I mean, so depends on what you want to do with it. Okay, what I mean by that is, at the most basic, an image is just a set of pixels, right? Now, I could store one number corresponding to each pixel. That would not be very efficient because this screen, for example, most of it is white. So why should I store so many pixels saying white, 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 white? I could probably do some kind of compression. But what kind of compression? There are multiple different types that you can do over there. One of them is called lossless compression, where it will give you back this exact same image, right? So PNG, for example, the PNG images are lossless. You take an image and you compress it with PNG, it will give you back exactly pixel by pixel the same image. JPEG is lossy. Okay, so JPEG, if I take this and I actually put it through JPEG and I come back, I'll probably find that all the lines are a little bit blurry now. Okay, so that's why I said that it depends on your use case. If you are trying to store photographs, JPEG makes sense, and in fact it is meant exactly for that kind of application. But if you are trying to store, let's say, line charts or something of that sort, you need to store it in PNG or some other format. You might even have vector formats where it actually sort of stores the lines that need to be drawn rather than each individual pixel. So PDF is like that, where it actually allows you to redraw and you can zoom in as much as you want and get more clarity. Okay, so on the other hand, for something like face recognition, it doesn't even do any of that. What is usually done is that as soon as it takes the picture, it then sort of extracts certain things called features, which are a set of other numbers which are related to your face, and only that is being sent to the server for the recognition. See, everything at the end of the day is bits. So byte code is a different story. All of these things are bytes, right? So as far as I am concerned, I'm looking at it from the hardware point of view. Everything is a byte. Okay. Yeah. I mean, that usually will completely destroy it, right? Because see, a neural network is trained assuming a certain sequence of layers. If you change that sequence after training, it completely destroys the network. I mean, like no guarantees at that point. Yeah. Yeah. Correct. Yeah. So you see, after you have done that, for example, right? Okay, whatever, any one of these. After you have defined the sequential thing and then you go through a training phase, right? And then if you change the order of the layers, it's completely, all bets are off. You are probably going to get like complete garbage as the result. But if you change it and then train, you may or may not succeed. And the reason I'm saying may or may not is because, this architecture was chosen for a reason. People said that, and out of experience, people have decided that, this convolution followed by a pooling followed by another convolution. Yeah, it's not convention. So that whole area of deciding what the structure should be is like a major area of research called neural architecture search. Okay, and that itself has, there are a number of PhD theses on that have been published, right? So it's not an easy problem to solve, and each problem requires a different neural architecture.
Is it by trial and error?
Yes and no. And what I mean by that is the final thing will require some trial and error. But there are some sort of good guidelines that tell you that generally speaking, you need to have this kind of a structure in order to extract certain features. You need at least this many features in order to get this kind of accuracy. So those are sort of known at a high level. After that though, the details of the architecture, there is some amount of trial and error involved. In fact, so they don't call it trial and error, they call it hyperparameter tuning. Okay, and that's actually trial and error. So yeah, it's the same thing. Yes. Yeah.
On the hardware level, do you have any disadvantages if you increase the frequency? Like
Power consumption.
cycle that increases per second, if it increases to a very huge rate,
Yeah.
is there any disadvantages? Does it affect the data?
No, see, every processor will have a certain maximum frequency that it can operate at. That maximum frequency is determined by something called the critical path of the hardware. Okay, so that's actually the transistors internally can't switch faster than a certain rate. So at that point, if you try going beyond that speed, your data is wrong. You fundamentally start seeing errors. It won't even be able to add two numbers together at, so let's say you have a CPU that's capable of running at 2 gigahertz. You somehow change the clock and try to make it run at 4. It can't even add two numbers together. Okay, but even running at 2 gigahertz, you don't want to do that all the time because that consumes more power. It starts heating up, right? So for example, your phone, what you will find if you use one of those CPU apps on it, is that most of the time it's actually running at 600 megahertz or some lower speed, right? And the reason it does that, the reason it sort of tries to lower the speed over there is simply to reduce the power consumption and thereby the heating, because otherwise your phone will overheat, the battery will get consumed very fast. So there are a lot of side effects of increasing the speed.
So can you talk about your research area of architecture of machine learning for robots?
Broadly this, exactly, right? So in fact, the question that came up about if I have an algorithm like this, so in fact, one of the things that I'm looking at is something of this sort. It's called image segmentation, right? And the problem that we are looking at is it's a fairly straightforward network architecture. You run it on GPUs and you find that at some point, the GPUs are not being utilized to their maximum extent. And literally what I'm looking at with some students and in fact jointly with another company is precisely this. How can you modify that architecture? Or are there compiler level tricks that can be applied or some other changes that can be done, which will give you a better utilization of the hardware that you have available to you? That's one part of it, but yeah, and that's broadly the area in which I work, which is trying to extract more out of the available hardware.
So in practice, what percentage of CPU utilization is needed to be exceeding the?
No, that's completely application dependent. So if you look at, yeah, so I don't know whether there is anything which is sort of considered as an acceptable thing. That would depend on your use case.
Applications, right? When we deploy the application,
Huh.
so if it is more than 70%, which will have another concern.
Yeah, I think you're ultimately, so that's the point. At that level, you are moving out of research and into engineering, right? So that's the difference between academia and engineering. In engineering, you have to just put a rule of thumb and say, look, this is getting tricky. I think I should have another machine out here to handle it. That's the only way it works, because I could sort of sit there and try and optimize and say I should be able to squeeze out an extra, so many this thing out of this processor. But bottom line is that it might fail at the critical point. So you don't want to take a chance. So you usually say, okay, around 70%, and then yes, immediately scale. So yeah, to give an example for this problem that I was talking about, where you have the image segmentation, ultimately the reason why we are looking at it was we were seeing something like around 10% of the maximum capacity of the GPU. But what even the company people, what they said was, look, we understand that the problem itself is difficult, because what ends up happening in that scenario is the image size is being changed quite a bit as it goes through the layers in the network, which means that the memory can never be fully utilized, right? So once you take that into account, what they said is, look, we are not even looking at 70%. If you can get to 30 or 40, we'll say that, okay, this is a decent use of the GPU. And yeah, let's sort of stop at that. But at least at that point, we should be able to say, look, why is it 30 or 40? Because there is this memory bottleneck, right? And in some place out here, I know that this is the reason for things being slow. I'll just accept it and sort of leave it at that and move on.
Is it possible to target some layers on some CPUs and other layers on?
Absolutely, yeah, a lot of people do that. So, yeah, there is a lot of research on that, plus also engineering, people do that all the time. So, in fact, the interesting thing is something like TensorFlow does part of that automatically. If you have an NVIDIA, yeah, some of it is automatic, some of it you can control with the code. But TensorFlow, for example, the NVIDIA libraries for GPUs, TensorFlow automatically decides what part to put on the GPU, what part to put on the CPU. It does some kind of a partitioning like that at runtime. And there are a whole bunch of libraries. Google has this thing called XLA, which is a compiler framework, which literally takes TensorFlow input and breaks it up into different things, saying this runs on a CPU, this runs on the GPU, and eventually I guess this runs on an FPGA or something like that. But right now it's mainly CPU, GPU that they do. All right, so thank you all for being here. I hope this was useful in some way, and I hope you enjoy your stay here. Okay, great. Have a nice time.